Hello. Today we're going to talk about a broadband gallium nitride power amplifier MMIC design. Gallium nitride processors with transistors suitable for operation at microwave frequencies are now commercially available from a number of foundries. Gallium nitride transistors have a higher breakdown voltage and maximum junction temperature and are particularly suited to the realisation of high power amplifiers. The output power of a power amplifier is proportional to the transistor's supply voltage squared divided by the load resistance. If we wish to increase the output power, we can increase the supply voltage or reduce the load resistance. Reducing the load resistance means that the associated matching network will become more lossy and have a narrower bandwidth. So, increasing the supply voltage is preferred. Gallium nitride transistors allow us to significantly increase the supply voltage due to their high breakdown voltage. A gallium nitride power amplifier will have around 5 times the output power of a PA MMIC power amplifier operating over the same band. The design we're going to look at today is a power amplifier operating over the 2 to 18 GHz band. It has flat gain and high output power. It uses the non-uniform distributed power amplifier architecture, or NDPA. It is designed on a gallium nitride on silicon carbide process. This is the schematic. The RF input is here. The RF output is here. The gate bias is applied here, and the drain bias is applied here. It uses 10 transistors. Each is in common source configuration, biased in class AB, and they run off a 30 volt supply voltage, which is applied here. Now, in a distributed amplifier, the upper operating frequency determines the maximum size of the common source devices. The main parasitic capacitances of the devices, that is CGS and CDS, are absorbed into gate and drain line low-pass filters. These low-pass filters are typically terminated in their characteristic impedances. Now, CGS is the larger of the two capacitances and determines the maximum size and hence output power for a given upper operating frequency. If we wish to increase the power without compromising the upper operating frequency, we have an option, and that is to introduce MIM capacitors in series with each device gate. There's one here, one here, one here, and so on for each of the 10 devices. Now, these allow us to increase the size of the device, yet still work to 18 GHz. They effectively reduce the shunt capacitance of the gate line low-pass filter, so extending the cutoff frequency. In a distributed amplifier, as we apply the input signal here, it propagates along the gate line toward the termination resistor. And as it does so, it gets progressively attenuated. This means that the device nearest the input is driven harder than the device near the output. So, under large signal conditions, this device near the input will compress sooner than the other devices. One technique that we have used is to taper the value of these series MIM capacitors such that the drive level on each device input is equalized. So they all compress together, which is far better for large signal performance. Now, in a conventional distributed amplifier, the device drains do not necessarily see their optimum impedance for power. We have tapered the drain line characteristic impedance so that they do see close to this optimum impedance for power. This is the drain line here. Notice that the drain line termination resistor is not required in our design. I'll now show the layout of our design. The RF input is here. The RF output is here. The gate bias is applied here. And the drain bias is applied here. Now, for a 1mm device on this process, in common source configuration, biased in class AB, running off 30 volts, the optimum load resistance for power is around 100 ohms. If we look at our drain line again, starting from the output, working backwards towards the input, its characteristic impedance increases. What we're trying to do is ensure that each device works into this optimum load for power. In doing this, the microstrip lines in the drain line get progressively thinner and thinner. There is a limit on how thin we can make these microstrip lines. For this reason, this far device near the input is made larger than the other 9 devices. This reduces the required load resistance at this point, enabling us to realize this thin microstrip line without breaking the process design rules. As this device is larger than the other 9 devices, this is why our amplifier is a non-uniform distributed amplifier. Care must be taken to ensure that the thin microstrip line can still handle the expected current. Care must also be taken in the design of the drain line bias choke. It must be able to handle the peak drain current, and it must have enough inductance to provide adequate impedance at the bottom of the band. Where the drain bias choke is applied is also significant. It is applied at the output, which is a low impedance point, so minimizing loading effects of this choke. Also, the drain line is at its widest, which is best for current handling and minimizing IR volt drops. We've now covered the main features of our design and the reasoning behind them, so we can now look at the simulated performance. Here is our test bench in which our NDPA design has been placed. The test bench can be configured for small signal simulations, such as S parameters useful for gain, return losses and stability. It can also be configured for large signal, such as power at 3 dB compression and the associated power added efficiency. So first we'll simulate small signal. Simulation's finished. We just take a look at the results. So this red trace here is the gain. It's 10.5 dB plus or minus 1 dB across our band. This blue trace is our input return loss, This is better than 15 dBs across our band. And the pink trace is the output return loss, which is better than 20 dBs across the band. Stability factor is simulated up to 30 gigahertz, and this shows that the amplifier is unconditionally stable. We'll now configure the test bench for large signal performance. The simulation takes around 45 seconds. Okay, the simulation is finished. The red trace is the output power at 3 dB compression, and this is 39 dBm plus or minus a dB across our band. The blue trace is the power added efficiency at the 3 dB compressed output power. This is better than 22% across our band and approaching 40% at the bottom of our band. This concludes our look at our wideband gallium nitride power amplifier MMIC. For more information on the design of MMICs, please visit our website at www.plextechrfi.com.